so bright. This is a brand new thing. Okay. Distributed load is not an evenly distributed load, it's varying along the length, as we've seen before. Here we're not just solving for the reactions, but we're also solving for the shear and moment diagrams, right? Whereas before, when we saw something similar, it was just the reactions we solved. And the intensity at the right is 13 kips per foot. At the left, you can see it's 0. So let's take moments about B. Clockwise moment about B is reaction A times 67. And then that's going to equal the counterclockwise moment from the varying distributed load. So it's 13 times 67 over 2. That's the total force applied down. And then we just multiply that by the moment arm, which is 1/3 of the length, right? So this is the centroid. That's that 1/3 of 67. Centroid of the triangle. It's over here. So for some of the cases we've seen before, you don't have to write shear and moment equations. It's pretty straightforward. There may be one single data point that we need, and we can draw the shear and moment diagram. In this case, we do know that the moment is 0 here and here because of the end conditions, the boundary conditions. The fact that the beam is deflecting and rotating here as it comes into both supports indicates there's no moment there. There's nothing stopping it from just rotating. Okay? So we know that, but because of the complicated distributed load that's not evenly varying, we need to write shear moment equations to get a plot what's happening. So I have, I'll write it over here, the shear expression is the reaction A the shear is, at the beginning, it's just the vertical reaction as we go into the beam, and then it's minus whatever's happened up to that point, so it's minus W x over 2. W up to that point, right? So that's the, if I'm taking a cut here, the shear, internal shear at that point is this force minus the total force that's occurred up to that point, and that's the W at that location. So the W times the x over 2 is the area of that triangle, which is the force down. So that would be the shear in that case, and then W, W is 13 over 67 times x. So it's this divided by this multiplied by any distance. If x is 0, then the W is 0 over here. So it's right here. That's correct. At this point, the intensity of the distributed load is 0. At x is 67. The distributed load, we put in 67 here, that cancels with that, and you get 13 kilojoules. That's at the right. And then it's a linear variation. So we have, this is the right expression for the distributed load, and then that W is this W, right? So this is equal to reaction A. Okay, I'll put in what the reaction A is then. It's 145 minus W. W is what's varying. 13 over 67 times x. That's W. That's W at any given location along the length. And then multiplied by x over 2. So the shear stress, the shear force expression is 145 minus 13 over 134, and then it's x squared. So we can draw here the shear diagram. We know at the left it's 145 at that point. So whereas the moment is 0 at the left, there's a shear force, right? Just as we come into the beam, we got shear force. And at the right, we know it's 291, but it's minus 291, right? For the same reasons given before, our definition of positive shear. So here we have minus 291. And then because of that square term, looking at this expression, so it's 145 minus that. If we put in x here of 67, we get back minus the 291. So it looks like this. Something like that. It's a little misleading. I'm going to redraw it. Further down. Better like that. So your shear diagram is not a straight line anymore, it's curving. And it starts out horizontally because if you look at the equation, it's 145 minus this square. So, and then it's an x squared, so it gets more powerful the further you go. That's what you're seeing with this parabolic diagram, the shear diagram. Let's find this location. We'll call this A. The shear diagram. That's going to be important because the slope of the moment diagram is equal to the shear force. And so where the shear is 0, that will be where the moment diagram has a 0 slope. So it will be the maximum. So minimum on the shear diagram is going to be the maximum on the moment diagram. Okay? In this case, when I say minimum, I mean the 0. So we have the equation here. So we just set B equal to 0, which is, this is your shear, so this is the point at 0, and we can solve for A. The x we get out of that would be that A distance, right? So we have 145 minus 13 over 134. X squared equals 0. So you get 13 over 134. X squared equals 145. And x then is 145 times 134 over 13 square root. Which gives me 38.7. That's A. Because x was starting from the same location, so this is 38.7. So now let's draw the moment diagram. Here for the moment, we're going out a certain distance x, this is the moment, and so we're saying that the moment is this reaction A times multiplied by x. That's the moment contribution from the vertical reaction at the left. And then that's clockwise, and then we're going to subtract the moment associated with this little triangle here up to that point x, any point x, okay? So again, this is the W, so you get minus W, the height, times x over 2, which is the area of this little hatched triangle. And then you multiply by this distance, the centroid from here to here, that's always going to be x over 3. So that should be what we have there. R sub AX minus WX over 2, x over 3. And then we have to recognize that W, at that given point, the intensity of the distributed load varies as a function of x also. So it's 13 over, we have W, it's 13 over 67x. W x squared over 6. Let's put in reaction A, 145 by x squared over 6. So in this case, we're going to have an x cubed term. You see that? So we have the moment is 145 times x minus switch from fractions in my notes to decimals, minus 0.0323 x cubed. That's just 13 over 6 times 67. Right off 323. 3 significant figures. M max at x is 38.7, right? B. So M max is 145. We're using the same equation here. Times 38.7 minus 0.0323 is 38.7 cubed. It's 3,740 kilofeet. Here, let's write capital A and B. Here, this is 10 feet, and then continues on another 3 feet. The deflected shape, now this is interesting, the left side's a pin, and the right side, not the full right side, but a V is a roller, but it continues over the roller, and there's a load here. So in this case, since this is the end of the structure, it's a pin, there's going to be 0 moment. But then over here, there's a force times this distance is 3. So there is a moment that this is continuing over that roller, this beam. So there is a moment in this location because of the bend, and we know what it's going to be. It's 5 times 3. It's 15 feet. It's negative. The deflected shape is something like this. Okay. So it's kind of like if you put a board over a single brick and you stood on it with one foot on either side like that, okay? And it would deflect. If you just think of this part of it, like that, you put your foot on one side, you put your foot, so it's balanced, the moment. Across the bed, it's bending like that. If it's bending, if it has curvature, it's got moment in it. So it's got bending moment as it's coming across here. As it's, moments of B, 0, so I have R sub A, that's 10, plus 5 times 3 equals 10 times 5. So, summing the moments about B, I have R sub A, that's 10, that's clockwise, plus 5 times 3 is also clockwise moment, that equals the counterclockwise mode of 10 times 5. Reaction A is 3.5 kips. Summing forces in the y is 0. We have arson plus 3.5 equals 10 plus 5. So reaction B, I get 11.5 kilos. 15 down, 15 up. That looks reasonable. Then we can just go straight to the shear diagram. For something like this, we don't need to write a bunch of equations in terms of x for the shear or the moment diagrams. Okay, so it starts at 3.5, right? This is the force up at A. And at all cross sections, that is transferring that shear from one cross section to the next. Nothing stopping it or making it change. So it's 3.5 until we get to here. I'll write it up here. And then as we cross the load in mid-span of 10 kips down, it's 3.5 now, which is up minus 10. So that gives me a minus 6.5 at mid-span, so it drops down like that. And then, as we cross B, there's a reaction up of 11.5, so you add 11.5, which will give us back minus 6.5 plus 11.5 is 5, so it goes up, and then it's like that. And then this is the, of course, if you go from the right to the left, you can see it's 5 because we're applying 5 kips down, so it makes sense, right? It has to converge as you go from left to right or right to left. It has to be consistent, so you get 5. This is your shear diagram. So we went from the left to the right, and we drew this, which is the typical way. But if you go from the right to left, this is 5, and then it's 5 minus 11.5 as you're going in, so that gives you the minus 6.5, and then plus 10 gives you the 3.5. And remember our definition of positive shear. If we take a little slice out, this is our definition of positive shear. So when we're coming in here, we're looking at this left side. You see that south? That's positive. When we look at this side, again, I'm going to draw this as positive shear. Right? Up on the left, down on the right, is positive shear. You can see here, when I'm coming in, that this is in agreement with that. So that's positive shear. And this on the left side, so that's also positive. And I'm going from left to right or right to left. Let's solve for this. This is interesting right here. That's the point of inflection in the deflected shape. And that'll be 0 moment location. Inflection. So let's sketch the, I'll erase this. sketch the moment diagram. So it's 0 here. It's 0 out here at C. This is where a vertical load is applied, so there's no moment there. No moment here, but there will be moment as we cross over here. The bending moment in this location here is this force times that distance, so that's 3.5 multiplied by 5. That's 17.5. So again, as I go from A to the middle of the span, it's 0 here. The force times any distance is the moment. So when I get to here, it's by that point it's 3.5 times the distance, 5. 5 here. Right. So it's this force and that's just a straight line because it's increasing in proportion to the distance. And then we can from here. Let's move this over. This is 0. This is negative bending here. You can see the negative curvature. So when the curvature is like that, negative, the moment will be negative. This is all positive bending, as we've seen from the first part of our sketch. And then if there's a transition from positive to negative bending at that point of inflection. The moment right here is just by statics, 5 times 3. That's minus 15. That's this point here. And then we can just draw a line between them. And then we want to solve for, so this point of inflection, that's this point here. It's when the moment changes from positive bending, this is positive, to negative, right? Moment and curvature are proportional to each other. So the curvature is a change in slope with respect to x, so it's this is positive curvature, this shape that's downward like that is negative curvature. And this point right there is right where it changes. And so that's this point here. So this is here, 0 moment equals point of inflection. And we can use this to solve this drawing, to solve for that point. This is A, B. So we'll call this distance A, little a, which is the same as this. So little a, this divided by this moment, absolute value 15, is equal to this whole distance from here to here, which is 5 over 15 plus 17.4. So solving for A, it's, that's just similar triangles. where it's switching from negative bending to positive bending. It's really important to know that because if you're designing, let's say, a reinforced concrete main span for a bridge or a beam, a big reinforced concrete beam, when you have loading, it deflects down, you have curvature like this, let's say a simply supported beam. And so in that case, you'd have positive bending. The concrete will crack in flexure at the bottom, at the tension side, and the steel reinforcement, when it cracks, if there's no steel reinforcement, it just opens up and collapses. And so the steel reinforcement has to be on the tension side. When the moment switches, when it's bending like this over a support, negative bending, and now the concrete is in compression on the bottom fibers and tension on the top, it cracks, multiple series of cracks, it opens up, and then the main steel reinforcement in that case has to be in the top of the beam, not the bottom. And so knowing where it switches from negative to positive bending is very important. In a bridge structure, you have a lot of reinforcement here, down in the bottom, and then here, it would be all the heavy steel, longitudinal steel reinforcement, and the concrete would be at the top. And as you go through this point, there would be a transition. You'd see the reinforcement changing from one side to the other under this load. So, just to make sure it's clear, so the similar triangles, what I did here, it's easier than it may look. It's just saying this divided by this is equal to this whole length here divided by this plus this. So it's just using this similar triangles. And then, but then what's nice is you can solve for A, and then that distance there is the same as this distance, where otherwise you wouldn't know where that location is. So this over this equals this, this over all of this. This, hang on, this over this equals this over that. Same thing. It's because it's the same slope. So here we have a cantilever. I have a vertical load of 10 kips. But I also have a moment, an external moment. So it's external force, but I have an external moment applied in this direction clockwise, 100 kips. That is length 12 feet. You have to be to determine the reactions. There will be a shear reaction and a moment reaction. This is R sub A and M sub A. Deflected shape, greatly exaggerated like that. Now it's interesting, if we just had 10 kips applied, it would deflect down like this, but it wouldn't continue having changing curvature, but because we also have a moment at the end, there's a moment at the end. So the slope is still changing right up to the end. Now, reaction A, what's the reaction at A? What do you think? What? Give me a number, say it. 10. Yes, 10 kips. So this is a moment, it's not a force, right? That's the force. So when we sum forces in the y, so you have to trust the statics. Okay? We're applying two things on the right side of B. We're applying a vertical force of 10 kips and a concentrated moment. But this is a moment, not a force. So when we sum the forces to get reaction A, it's just equal to 10 kips. Yes. Okay? We're not adding in that moment of 100. But when we solve for M sub A, we have this moment on the wall is 10. This is the vertical load applied, multiplied by the distance of 12. That's 120. Now, this is a moment, so we have to add that too. Okay, so plus 100. So that's 220 kips. draw the shear diagram. Is it positive shear or negative shear? Is it constant or is it changing? Anything? Any response from anyone? I'll be happy. You can say the wrong thing, it's okay. Well, if you take a cut right there, you can see it's 10 kips and it's positive, right? So remember our little definition of positive shear? This, right? If I look at, if this cut is right there, this force is up, this is definitely positive shear. There's no force along here that's changing it, so it's going to be constant over the length of this. 10. That's it. That's our shear diagram. And then the moment diagram, that's going to be interesting, right? Is it negative or positive moment along the length? Or does it change? Remember our definition of positive bending is this. So that's the definition. Positive bending, and it causes a curvature across the section like this, shortening the fibers above the neutral axis, extending them below. So that would be positive. This is negative. It's in the opposite direction. At all locations, the curvature is the opposite to that. So just visually, based on my approximate deflected shape, it's greatly exaggerated vertically. You can see that it must be negative curvature. So let's draw the moment diagram. So it's negative bending. It's negative curvature is negative bending. Right moment. At the left, so at the left I have minus 220. You see how it's this way? It's opposite to our definition of positive, so it's minus 220. And at the right, what is the moment on the right? What at B? This is A. At B. What's the bending moment right here? It's right there, it's staring at you. It's minus 100, right? So we have this. And in between, it's just a straight line. Out for this, it was a little complicated because we had these two different things happening on the right. We didn't have to write, I didn't write an expression for the shear or the moment diagram. It's more a matter of understanding, right? It's only when we have these complicated distributed loads that we have to typically write equations. Or if we want to solve for displacements, which we won't be doing in this class. Yeah.
For the moments of A, how do you get the 10 by 120?
Moment at A,
Yeah.
it's from this force. So it's that force multiplied by 12. Is that what you're saying?
Yeah.
I guess I was doing the math in my head as I was writing it. 10 times 12 is 120, so it's like new math. I already wrote it in there. Yeah. Okay, so that's 10 times the distance 12 plus the 100. So is that okay? That still adds up to 2.
Because I saw 120, then I got lost.
Yeah, me too. Now that I see it, yeah.
Explain like the points of negative 100 and 220 on the moment diagram.
Say that one more time.
Like, can you explain how you found the points on the moment diagram sometime?
Well, here, the moment right at this point has to be 100 because you're applying 100. And you're applying it this way, which is opposite to this when you look at the right side. So it's minus 100 this force down, yes, it applies a shear directly, like as soon as you move into the beam, it feels that whole force of 10 kips, like our shear diagram shows. But there's no moment contribution from the applied force at this location. It takes distance for this part to develop. So the only moment at B is this external moment like that, cranking like that. So it's putting minus 100 right there. And then on this side, if you take a cut, the only moment is this reaction on the wall, which is minus 220. Which you can see again, looking at this, our definition, that's positive when you look on the left side. So this is the opposite of that. So you write minus 220, and then it's just linear between that. If you do write an expression going from the left to the right, you have the moment is 10 times x. So that's from this reaction times any distance x minus 220. That's the expression for the moment across the length. The shear is just 10. And you can find the shear, you can take the derivative of this, and this goes to 0, this becomes 10. Does that answer your question? And then when you put in, for your moment expression, if you put in x, any value of x, you'll get back the same moments here. So x is 0, you get minus 220. When I put in x is 12, and then we get minus 100. Okay, that's a good stopping point for a few minutes, so I'll be back in 10 minutes.
Because right now, it literally feels like I'm just copying shit down. I think once you watch the video, you'll be okay. You'll be okay. Okay. Then listen to the song.
We're going to switch topics a little to centroids of areas, different, and this translates to centroids of math. given area, where is the centroid? How do we- We'll start with the rectangle. The white bar, we're gonna find the centroid in two directions here for the rectangle. Look at it for other shapes as well. So we're going up this way, and we're finding, in this case, we know for a rectangle, the actual centroid is gonna be halfway up and halfway across. And so it's gonna be right there, right in the center of this thing. But other shapes you don't know ahead of time. So we'll start with this and make sure we get the right results, and then we'll look at other shapes. So we have the interval of y dA over the area. So we have the integral, and I'll put the limit in a minute, of y times dA, and now we're gonna substitute this dA down here as v dy. And so now instead of integrating across dA, I'm integrating across y, right? So I'm gonna go, my limit on y starting down here going up to here is from 0 up to h. From 0 to h. And then this is the integral dA, which is v dy. From 0 to h. I can take out b. Mostly I get b integral from 0 to h y dy divided by b integral from 0 to h dy. Continue on this next board. You can see b cancels in this case. So I have y bar integral from 0 to h y dy over the integral from 0 to h dy. So this is just y squared over 2 from 0 to h divided by the integral of dy is y from 0 to h. So that's h squared, putting the limits in, h squared over 2. Divided by h. One of the h's cancels, and you can see you get, therefore, y bar is h over 2. Which is expected when we look at a rectangle. The centroid, there are two positions of the centroid. One's vertical, and one's in the vertical direction, one's in the horizontal. Because it's an area, right? And it's not just an area, but it could be if you have a thickness of a steel plate, let's say, this would be not just the center or centroid of the area, but it would also be the centroid of that steel plate, whatever you have, right? And that's important. Right now, I have people down in the lab moving that big, if you look at that big frame down to the right, that I said they're modifying, so we get that large column or other thing. They're moving the reaction wall and that what's going to be the tall vertical member. And they're doing that this morning and last night. My sort of job was to find out where the centroid of all those different steel plates were made of this member and set it to them, because there was a possibility you have the frame and then that big beam that they're connected to the front. The beam is hanging out in front of the beam. It's not supported on the ground. And it's so heavy, it was possible that when they attach it, it's going to flip the whole thing over to the front. And so last night, I did this and sent an email to the guys working in the lab that, okay, this is the centroid is, I told them 16 point something, 16.3 inches back from the front bottom toe before that big beam is on the front. And it turns out when I included that, it shifted the centroid of this whole thing to 8 inches behind that front plate, but it was still such that it shouldn't, on its own, it shouldn't fall over. But I also warned them they're going to be using forklifts and other stuff that don't tilt it. Because as they do it, if they tilt it, that tall vertical beam that sticks up about 11 feet in the air will lean forward, and the centroid then of this thing, when it's rotated vertically, if the back lifts up at all, that front will lift and the centroid will shift beyond the front and the bottom of that steel plate, the front of and the whole thing will topple over. You know, it's over 10,000 pounds. So the big reaction wall, 7,000 pounds, the vertical beam, 3,500. Combined is 10,000 pounds, and of course it's the same as So anyway, centroids, and I did this by hand. You know, this was last night. There were about 30, 40 different steel plates I had to include in my calculations. So last night working on this. So you know, some of them are 2 inches thick steel plate, and I had to add up all their weights. And this is in 3-dimensional geometry too, not just 2D like this. So my point is that, you know, knowing centroids, not just of areas, but of weights of plates and so on, is important, right? Makes a difference. So in this case, the vertical position, this is h over 2, as expected. It's a simple rectangle. And now let's look at the other way. So that's y bar, and then this is x bar over here. Because it's a simple rectangle, you know, it's just b over 2, but that's one. X dA over area over the area, which is the same as dA. And then this is the integral of x. Now the dA, instead of this differential area, we're going to write it like this. This is equal to the height, right? H multiplied by dx. Whereas this one was d dy, h dx. So we're going to be integrating then from 0 on x to b, right? And then divided by, in this case, dA is h dx. So we're going to go from 0 to b. And then we can take out the h. Cancel. And we have x bar equals the integral from 0 to b x dx over the integral from 0 to b dx. This is equal to x squared over 2 from 0 to b over x from 0 to b, which is b squared over 2 divided by b, and therefore x bar, that's the centroid in the horizontal direction, is b over 2. As expected. So it's halfway along the width and halfway up. Is that clear? Now let's look at something that's a little more challenging. Let's look at a triangle. our centroid, it's like we had one here. Again, this is the point where if you cut out an area, the big cardboard, you have plate, you put it in the horizontal position, you put your finger in it, that's the balancing. So this width is V. You can see by symmetry that this is a V over 2. But what's not obvious, without me telling you ahead of time, that where the centroid is in vertical directions, that's what we have to solve. This is our Y bar. Here's Y, and this is dy. This is dA. And this distance from here to here is W. The width. So dA is W dy. Total width dy. Y bar is the integral from 0 to h of y dA over the integral from 0 to h this is the integral over the area, and this is dA. So this is the integral y w dy over the integral w dy. And now we can say from 0 to h. Hang on, there's an error here. W came, so I can't pull it out of here. Let's see. Okay, what I've got. integral of the differential area over the whole area is the area which is just b times h over 2 because it's a triangle. So that's fine. And then it's the other part that I was W, we have to figure out what that is. And so this is from 0 to h now. W, we have the width here, so it's b minus b over h times y. So the width W as a function of y is, we have b, and then it's minus b times any distance y over height h. So in other words, when y is 0, this is b, the w, the width, and then as y increases, this decreases, and then finally, when y becomes the y position going up, becomes h, that cancels, and you have b minus b, which is, at this point, w is 0. When y is 0, this cancels, and you get back b, which is the width at the bottom of the triangle. So this is the correct width as a function of the position of. So we can take out b times 1 minus y. So then this equals the integral from 0 to h y times w, which is this, so it's times b 1 minus y over h dy. I take the b out, I take the y in, have the intervals from 0 to h, and then it's y minus y squared over h dy. So that's how we can integrate. So we end up with b y squared over 2 minus y to the third over 3h from 0 to y. This is b, and then now I'm putting h in for y. So I have h squared over 2 minus h cubed, but there's an h there, so I'll cancel that. H squared over 3. So this is bh squared. This is 1/2 minus 1/3, so 3 minus 2 over 6, so over 6. So the total y bar, this top part we just found is bh squared over 6. And then the bottom part is just the area of the triangle, bh over 6. So we're going to end up with 2 over 6 is 1/3. So therefore, y bar is h over 3. That's how we know that the centroid of the triangle is at the 1/3 location. And that's true if you have a triangle like this too. This is A, this is A over 3. And let's say this is B, this is B over 3. Okay, that's where the centroid is. And in this case, because of the type of triangle it is, vertically, so you act like a triangle is still longer. Here's the half circle. We want to know the center of that. So this is not obvious, right? Again, the question, this is the area is not a full circle. If it's a whole circle, you're right in the middle of the center. This is a half circle. And again, for all kinds of reasons, we need to know what the center of the shape are. So the centroid will be, somewhere like that, right? Again, imagine cutting this out of a piece of cardboard. This is the balancing point. So you cut the shape out of cardboard, turn it flat, and then you say, where would you put your finger? So it's balanced in all different directions. That's the centroid of the area, if you imagine it. Yeah.
Sorry, I got a question over here. Should it be h cubed over 3? I could be totally wrong.
The, where? Tell me where. Here?
Yeah, right.
Yeah, I could get an h here. Right, so you put in the limits, that's h cubed, like you're thinking, but then it's divided by h. It has to be h squared because it's this squared, you can't add arguments now. So the units have to be. It makes sense that they're both h squared.
Thank you.
Here's my different area. Gradient up, y. this is r times the cosine theta, then this value up to that point, y is r sine theta. So we have the interval from 0 to r, y 2r cosine theta dy. So I'm going to put that as r sine theta. That's my y, and multiply that by 2r cosine theta. So we have y is r sine theta, so the differential of y with respect to theta is r cosine theta. So therefore dy, I have to move all this into theta, so dy is equal to r cosine theta multiplied by d theta. I'm just taking d theta to the other side. And so I'm going to substitute that dy as d theta. So then this becomes the integral from 0 to r. I've got, I can see 2r squared. I've got a sine theta, cosine theta, and then I got dy, which is r cosine theta d theta. So there's another, so this is equal to the integral from 0 to r, so the limits to r cubed. I can see I have a sine theta and a cosine squared theta. It was important that I change the differential term at the end from dy to d theta because I'm integrating with sines and cosine thetas. So everything had to be in the same terms. All right, we'll finish this next time. I'll post a homework later today, and then